going to be talking about the naive Bayes algorithm. So naive Bayes classifiers are a family of simple probabilistic classifiers based on applying Bayes theorem, and we will assume strong assumptions between the features. So let's take a look at the Bayes theorem. So as we can see here, using the Bayes theorem, we can find the probability. As you can see here, we have the conditional, this is the conditional probability formula. So conditional probability goes like this. Using Bayes theorem, we can find the probability of A happening, given that B has already occurred. B is the evidence and A is the hypothesis. We make the assumptions that the features are independent. That is, the presence of one particular feature does not affect the other. So when we are using the naive Bayes algorithm, let's say we are trying to predict the outcome between two features. So the naive Bayes algorithm assumes that these two features are independent. They are not the same. So that means that if a change occurs to one particular feature, that doesn't affect the other feature. But in reality, we know that these features may have a relationship. But when we are using naive Bayes algorithm, we simply assume that there is independence between the features. So as you can see, using the naive Bayes formula, we have the posterior probability, we have the likelihood, we have the class prior probability, and then we have the predictor prior probability. So the prior probability describes the degree to which we believe the model accurately describes reality based on all of our prior information. And then the likelihood describes how well the model predicts our data. And then we have the predictor prior probability, or the normalizing constant, the constant that makes the posterior paper density integrate to 1. So let's say we are trying to predict, let's say, if an email is a spam or not. So when we use the naive Bayes classifier, it will predict that the email, maybe it predicts that the email is a spam, let's say by 0.80, and then not spam 0.20. So if we add those probabilities, they should all add up to 1. So that's the job of the normalizing constant. And then we have the posterior probability, which represents the degree to which you believe a given model accurately predicts the situation given the available data and all of our prior information. So let's take a look. Let's take a look at this data. So let's say we want to play golf, and then the data we are given here determines if we are going to play golf or not. So as you can see that golf is not suitable for us to play golf when it is rainy, hot, the humidity is high, and the wind is there is no wind. And then it's suitable to play golf if it is overcast, hot, high, false, and yes. So remember, when I first started the video, I talked about that the naive Bayes algorithm assumes that the features are independent. So this means that if the outlook is overcast, that doesn't mean that the temperature will be hot. No, the outlook can be overcast, but the temperature can be low. So there is no independence between the features when we are talking about the naive Bayes algorithm. But in reality, we know that there must be a relationship between these features. So you can see it is also suitable to play golf when it is sunny, the temperature is cool, the humidity is normal, and then there is no wind. So as you can see, so if we take this data and then we try to predict the outcome to play golf or not, so the naive Bayes algorithm will treat each one of these features as independent, and then we'll predict the outcome. So we make two assumptions here. One is stated above. We consider that these predictors are independent. That was what I was talking about. So that means that if the temperature is hot, it does not necessarily mean that the humidity is high. Another assumption made here is that all predictors have an equal effect on the outcome. So what this statement really means is that each of these each each of these features have an equal effect on the outcome. So let's say that time we had four features. So let's say each and every feature is 0.25 effect on the outcome. If we add all of these 0.25, it will give us one, which is the outcome. That is, the day being windy does not have more importance in deciding to play golf or not. So as you can see that one feature cannot determine our outcome, but all of the features have equal effect. So if that means that the outcome is overcast, that doesn't mean that we cannot play golf, but we need to use all the features to determine the outcome. So the variable y is the class variable that is to play golf, which represent if it is suitable to play golf or not given the condition. And then the variable x represents the parameter or features. So as you can see here, the variable y in our formula are the classes. In our case, it's one when when you when it's one when you play golf, and it's zero when you cannot play golf. And then x are the features. So our features, remember, x represents outcast, temperature, humidity, and then wind. So these are the features. So this is another formula of the naive Bayes classifier. So here x we can replace x with outcast, humidity, temperature, and then windy or not. So here we can say x1, we can represent our x1, which is, let's say, the first row, and then the class. And then if you can still remember, in our first row, if we take this first row, here we cannot play golf. So this will x will be the features outcast, and then the class will be zero. And then the next row it will be outlook, and then again the class is zero. And then here you take all these features x, and then y will be one since we can play golf. So what are the pros of using the naive Bayes? So it is easy and fast to predict a class of test data set. So the other thing is naive Bayes classifier performs better compared to other models when we assume that there is independence between the features. And the other thing is that it performs well in the case of categorical input variables compared to numerical variables. So what are categorical input variables? So categorical input variables are variables that represent a category. Let's say we say one will represent if it is overcast, and then zero will represent if it is sun. So these are variables that represent categories. The cons of naive Bayes is that the independent predictor assumption. So since the naive Bayes assumes that there is independence between the features, but we know that in reality there is a relationship between the features. So let's say if it's overcast, then the temperature might be cool. So in reality, there is some relationship between the features, of which in naive Bayes to predict that there is independent. And then use of the naive Bayes. So naive Bayes is used for real-time systems, for example, like credit card fraud prediction. And then we can also use the naive Bayes for multi-class prediction. And then it can also be used for recommendation systems. For, let's say, for example, if you go on Spotify and then you play a certain genre of music, and then the next time you open Spotify again, it will recommend another same song in the genre. So you can see that that's one application of the naive Bayes algorithm. So thank you for watching, guys. In the next video, I'll be demonstrating how to use the naive Bayes using programmatical. Demonstrating how to use naive Bayes programmatically. Thank you for watching, guys. Please subscribe and click on the notification bell so you can receive more videos like this every week. Thanks for watching.